Hello, my name is Olivia Martin, and this is my lab report for Physics 2211, Projectile Motion. In this lab, I explored how real-life motion of a projectile compares to two different physics-based simulations. This report brings together video analysis, force modeling, and computational thinking to better understand how Newtonian mechanics play out in real scenarios. The foundation of this lab lies in two fundamental physics ideas, Newton's second law and the momentum principle. Newton's second law tells us that the net force on an object equals its mass times acceleration, which we can write as F equals ma. This equation helps us determine how motion changes over time based on forces acting on an object. The momentum principle, expressed as delta P, or momentum, equals force times delta T, shows how momentum can change based on the forces over time. In a vacuum, the only force would be gravity, but in real life, we know that objects moving through the air experiences resistance. This is called drag, and we model it as force that always points opposite to the direction of motion, and whose magnitude depends on the square of that speed. That drag force, especially for lightweight objects, makes a big difference. To investigate this, I recorded a video of a loosely wadded up paper ball being thrown across the room. I made sure to keep the camera still in position to throw, so the motion occurred across the screen, not toward or away from it. I also taped a ruler to the floor to use a calibration tool later in the tracker. The paper ball had a mass of 0.02 grams, which is 2 times 10 to the negative 5 kilograms. I imported the video into Tracker and collaborated the scene using the ruler and placed the x-axis along the floor. I also set the origin directly below the initial position of the ball. Tracker allowed me to make the object's position frame by frame and extract the time, x position, and y position values that I used later for comparison with my model. My first computational model only included gravity. This is what we call an ideal projectile model. In this simulation, the only force acting on the object was gravity, constantly pulling the object downward at 9.8 meters per second squared. The motion followed a symmetric parabolic path, the kind you'd see in a textbook example of projectile motion. Using GlowScript, I coded the model to update the object's velocity and position using the formulas velocity equals initial velocity plus force divided by mass times delta t, and position equals initial position plus velocity times delta t. The simplicity of this model makes it easy to predict, but as we see, it doesn't match reality very well. The second model builds on the first by including air resistance. Here I added a drag force that grows with the square of the speed and always acts opposite to the motion. That means it reduced the ball's velocity in both the x and y directions. In the code, I calculated the speed of the object at each moment, used that to get the direction of motion, and applied the drag equation. By tuning the value of b, the drag coefficient, I was able to bring the simulation much closer to the real data. This model produced a more realistic, flattened arc and a noticeably shorter travel distance than the gravity-only version. Comparing both models to my experimental tracker data, the differences became clear. The gravity-only model went much further and higher than the actual motion. It didn't account for any energy lost into the air. The drag model, on the other hand, aligned much more closely with the observed path of the paper ball. The arc was shallower, and the ball landed where it actually did in the video. This comparison reinforced that the physics principles I use, like force vectors and Newton's laws, are effective when they include real-world forces. Even a simple object like a paper ball carries enough complexity to highlight how important modeling is in physics. Now let's imagine what would happen if I had thrown the object straight upward, using the same speed. First, the ball would slow down as gravity and drag work together to reduce its speed on the way up. Then it would stop momentarily at its peak before falling back down. Drag would still be working, now opposing the downward motion too. So overall, it would take longer to return to the ground, and it would reach a lower maximum height than it would in a vacuum. This shows how drag reduces both flight time and vertical range, especially for lightweight objects. It's a perfect example of how energy loss and non-conservative forces impact motion. In conclusion, this lab gave me hands-on insight into how physics concepts apply in both idealized and real-world scenarios. The gravity-only model was clean but unrealistic. The model that included drag required more effort to tune, but reflected actual motion more accurately. by combining video analysis with the computational modeling. I applied Newton's second law and the momentum principle step by step, not just on paper, but in motion. This lab helped me see how physics and coding come together to build accurate simulations and why assumptions like ignoring air resistance don't always work in the real world. Thanks for watching my report.